Some properties are important to read them from a graph of function. So the graph of function is a set of points x, y, where y is equal fx, when your x is describing the domain of your function. But we can define also a graph of curve. So graph of a curve. So a curve is not a graph of curve is not necessarily a graph of function. So it's more general. It includes more situations. So is it a set also of points x, y, such that um, x and y satisfy an equation, or the equation of the curve. Okay, satisfy the equation of the curve. Okay, so the equation of the describing the curve. Okay. Yes. Now, what kind of properties we can look for? We can read from a graph. We can look to the symmetry property. So symmetry. So we can see it. We have two properties. Even symmetry, or there are plenty of symmetries, but two are more important that we will see. We will see more often. So let's see. For example, at the same time, let's describe then through examples these properties. Okay. So here it is. For example, if I consider the function y equal x2, the parabola. Y equal x2, so I have, yes, the shape, the global shape is this one. Okay, so this is my function y equal x2. So I see that each time I have a point, there is something, um, a pattern here that is repeated. For example, I see that this half of the curve that is at the right, my right, is symmetric to the other one. So I can deduce one part from the other by using symmetry with respect of the x-axis. So we have a symmetry with respect of x-axis that we characterize. How we can characterize it? Each time you have a point EB, so okay, here B, so you have a point EB, then you can deduce the other point from the on the curve by taking the minus E and B. Okay, so symmetry, we have then symmetry about with respect to about the x-axis. So symmetry about x-axis, or let's write it here, symmetry about x-axis, y-axis. So is characterized by saying that EB belongs to my graph if and only if we have minus E and B also belongs to this graph. So you need to pay attention to this writing. That means also as a consequence, I will be looking for symmetry if I have a domain that is symmetric, because each time I'm considering E, I'm considering minus E. That means even my domain of definition should be symmetric. We have also a symmetry with about the origin. Okay, about the origin. So this is symmetry about y-axis. Okay, symmetry. Okay, symmetry about y-axis. We have another with respect to the origin. So an example for this one is the x3 function. So x3 function, the global shape is this following. So it does something like that. Okay. Okay. This is y equal x3. So a point here, EB, if you have E and B, then you obtain, if you look, it's symmetric with about the y, about the origin. Here is the origin. Then we will get something like that. Okay. So we need again here minus A, and we have also here the minus B. So the point minus A minus B should be on the graph to have this kind of symmetry. Let's try this using dots maybe. Okay, yeah, it's okay. So leave it like that. Okay. So yes, here it is. So that means these line segments cross the origin and in the middle point. Okay, and the two distances are equal here. So the characterization of symmetry about the origin is that EB belongs to the graph if you have minus A and minus B belongs to your graph. Okay. Now, in case you have a function y equal fx, you can check these two properties by checking that f at minus, so f at minus x is exactly the same. You see, the image here is the same, while here is the opposite. Okay, and here you have f of minus x is minus fx. So this is how we check for function if whether it is, we call it an odd function. This is an even function, and this one is an odd function. So this is the terminology that you should be uh, get used to. Okay. So for example, here, if for my function here, let's check for my formula. So this is my fx. Let's check the for if I have an even function. So minus x f power 2, okay, which is x2, which is exactly fx. While here I have f minus x, my formula, this is my formula fx. So it will be minus x, take it to power 3, but this gives me minus x power 3, which is minus fx. So I have an odd function, so I'm expecting a graph that is symmetric with the origin. Similarly, with symmetry with the y-axis. So those two are most important. There is another something else we can read on the graph. This one is the intersection of curve with the x-axis or the y-axis. So suppose, for example, another situation. Let's graph maybe another equation. Yes, another graph here. Let's imagine another graph. Okay. Okay. Yes, for example, just a line. Okay, what about this line? So this is passing through. So this intersection, there's 2 points. The intersection of the graph, okay, of my line with the x-axis is important. It gives me, there's 2 points, particular points. One of them, we call it the, one of them, this one, the intersection with x-axis, the x-intercept, we call it x-intercept. Okay, so it's the x coordinates that you, yes, the points, if you take your graph, intersect the x-axis or x, the line or x, it gives you the x-intercept, okay, with 0, okay. So we can, for this particular graph, you have just 1 point, okay, but sometimes you can get 2 points, okay. So maybe I should leave it open or with just dots like that. Okay. Now, the other intersection, this one also is important. This one is called the intersection with y-axis. This one is called the y-intercept. So you look for it how? You look for the intersection of your graph with the y-axis. So the y-axis, points on the y-axis have the equation x equals 0. Point on the x-axis have the equation y equals 0. Okay, that means you will look at the points that have their x 0, and you look for the y-intercept corresponding point. Okay, value intercept from your graph. Okay, there it is. So either we have a point or not. So let's, instead of, yes, this is the definition. My set can be empty if my curve doesn't meet one of the axes. The intersection can be empty. So these 2 points are also good to read and identify. Symmetry also. And yes, now given a curve like we introduced the graph of curve, knowing just given a curve, we can check whether it's a graph of a function or not. This can be done using the vertical line test. So we have vertical line test that is we can use when we are given a graph. So vertical line test, so it's like illustrate the definition of function to say that a graph of a graph, just a graph. So okay, a graph will be a graph of a curve of a curve is the graph of a function means we mean what? We mean that is described by an equation y equal fx if any vertical line crosses any vertical line intersects in only one point. Any vertical line intersects the curve in one point only. Okay, so let's imagine a line here. Let's imagine a line, vertical line, and move it along just visually. Okay, so so suppose I have a line here and try to move it along my curve. Okay, I see here each time it crosses my curve in one point. So this curve, imagine we repeat this. So it's a curve of function. Here also, if you move it, you see the intersection is only one point. For this graph also, it's a graph of function. Okay. Now, suppose I'm given a graph in this case, for example, this one. Yes, no, sorry. Okay. So, yes, why not? Let's graph one here. Use the line. So suppose that we have this graph like that here. Okay. What about this graph? Can I say it's a graph of function or not? I can have something like that. Okay. X and Y. So here I can, so let's make the test using the vertical line test. So you see, if I move my line, vertical line, I see it crosses in 2 points. Here, the only one here, it crosses at 1 point, the vertex here, but then for each x, I have 2 possibilities of y, so it cannot be the graph of function. Okay, so this one, I can answer that no, cannot be, cannot, uh, cannot be the graph of a function, graph of a function. So this is, so the test is practical when we are given a graph, and just make the test visually if it can be described or not with a formula y equal fx as a function. Okay, so those are the main properties you should know.